So homeomorphisms are the isomorphisms of topology, saying when two topological spaces are to be regarded as the same and how you regard them as the same. So formally, as you would expect in an isomorphism, a map f from x to y. So we'll take x and y as topological spaces. So a map is a homeomorphism. So a map from this, which means a function, is a homeomorphism if f is continuous and has a continuous inverse. So let me spell that out in a moment. Has a continuous inverse. First we just say it in these broad words. Inverse. So that is, there exists g from y to x such that f composed with g is the identity of y, I assume, because you have to start with y to apply g first, and g composed with f is the identity of x. Okay, so it is continuous and it has a continuous inverse. So this will give you a natural notion of isomorphism. And just to record some obvious facts here, first of all, identity of x is a homeomorphism. Here, of course, we assume x has a fixed topology. So if I look at the identity from the space to itself, it is a homeomorphism. And B is the composition of homeomorphisms. Homeomorphisms is a homeomorphism. Namely, you take the composition of inverses and put them in the reverse order. You would have seen this all the way from linear algebra, where if you have compositions of matrices, AB inverses, B inverse, A inverse, and groups, and everywhere else. So these two are considered elementary as far as this course is concerned. Another elementary thing is at set level, a homeomorphism is a bijection. And now our first example is a warning example. Okay, so what is not true? So in the case of group theoretic contexts and even linear algebra, if you have a bijection, which is a linear map or a homomorphism, it becomes automatically an isomorphism. This is not true in topological cases. So we note, let me just say, f from x to y continuous bijection does not imply f homeomorphism. So we always have an inverse and a unique inverse as maps of sets, but it need not be convertible. So example, I'll take X as a set with cardinality at least 2. I mean, I just don't want just an empty set of the whole set. Let's say X is set, X has cardinality 2, at least 2 elements greater than or equal to 2, and you take f from maybe I should better to call it S. And f from x to y with x having is S with discrete topology. So S is topology, and y is S with indiscrete topology. Now this is continuous for two reasons. Anything and f could be anything at all, but let's take f as identity. So f of s is S for all s in S. So I have two topological spaces x and y with the same underlying set S. So I could have called them S tau 1. So this is S tau 1 and this is S tau 2. So any function from discrete to indiscrete topology is going to be continuous for two reasons: anything from discrete is, anything to indiscrete is. But F inverse, so F is bijective and continuous. But F inverse is not continuous. Okay, this is a sort of drastic and in a way a silly example. Okay, so we'll just see a more interesting example of this as we next, and then we'll see examples of positive homeomorphisms as well. We saw what is a kind of silly example of something which is a bijection and continuous but not a homeomorphism. Here is a much nicer example. So let's take F mapping the half open interval 0, 1 to the circle. Okay, and I'm going to look at the circle as unit complex numbers z in C mod z equals 1. Or if you prefer, you could use trigonometric functions if you're not comfortable with complex numbers. X, y, x squared plus y squared equals 1. Okay, and f of t is going to be e to the power of, it's going to be e to the power of 2 pi I t, or t in 0, 1. And if you're not comfortable with complex numbers, this is just cos of 2 pi t and sine of 2 pi t. So we are taking a angle but rescale to be between 0, 1 to the set which is, so we have a half open interval here and we have a circle here, and we are simply mapping this point here to the origin, and then as we go along this way we wrap around the circle. Okay, and using a bit of either trigonometry or just elementary complex numbers, this is indeed a bijection. Anything on the unit circle can be uniquely written as e to the 2 pi t, e to the 2 pi it, or cos 2 pi t sine 2 pi t, where t is between 0 and 1. So this is indeed a bijection. Okay, so f is a continuous, let me just say that, so f is a continuous bijection. It's continuous because it's continuous as a map from R to Rn. We know that coincides with a usual analysis continuous. Okay, but F inverse is not continuous. Why is that? Let's do it in our topological sense. Let's take an open set containing the origin, this open set. Okay, and what is the inverse image of, so in terms of continuity, I'm sorry, so that has an inverse image which is open. That's not a problem. So if we do things in that direction, that's not a problem, because indeed the function is continuous. But now let's take an open set near the origin here. Okay, so let's take this open set. So this is an open set in the half open interval, because it's in the subspace or metric topology, whichever way you want to look at it, is the intersection of half open interval with the open interval, which is open in R, or you use the metric. This one, and if I look at, so this is, I'm looking at the map F inverse of, let's call this U. F inverse inverse of U. I've written it that way just to emphasize that is the inverse image under the inverse map. Okay, of U is going to be now the set which will be this way, half open here. But it will just end abruptly at this point, and that is not open because there are points that come to it close from this side. Yeah, so it is any intersection which contains this point of a ball with a sphere will contain some points just below the axis. So this is continuous bijection, but it's not continuous. So this is a more serious warning that even for perfectly well behaved spaces, homeomorphisms may not be continuous. We have to look at examples. First, let's just look at a couple of formal properties to note, rather a definition. We say spaces x and y are homeomorphic if there exists a homeomorphism from x to y. And the following proposition is just as easy as the previous one. Homeomorphism is an equivalence relation. Again, you can just think in terms of the specific properties we need. Reflexivity, space is homeomorphic to itself by the identity. Symmetry is given a homeomorphism, it has an inverse, which is also a homeomorphism. And transitivity is because compositions of homeomorphisms are homeomorphisms. So spaces being homeomorphic is an equivalence relation, and we think of these spaces as the same. For example, the following proposition is true. If f from x to y is a homeomorphism, and U contained in X is open, same will be true for closed and frontiers, etc., then f of U is open. Okay. And the proof of this is simply that let G from Y to X be the inverse of f. This is continuous. So then f of U is G inverse of U is open. Yeah. So f is G inverse. The inverse image as a set, but it's also the image under G inverse. So G inverse of U, it's f of U is G inverse of U because G is the inverse of f. So this is open. So homeomorphisms will preserve all properties. You can take as easy exercises. So closed sets have images that are closed again. So interiors of sets will map to the interiors of the images. Closures will map to the closures. Frontiers will. Any topological property, anything defined in terms of open sets, which is all of topology, is preserved under homeomorphism. For this to be useful, we need to see that lots of spaces are actually homeomorphic to each other quite often. And we'll also have to understand how they're not homeomorphic to each other. The latter will be topological properties, which we'll turn to next. But in terms of being homeomorphic, we will just construct a few functions and learn more ways of constructing continuous functions. And that will be the next video.